Okay, in this video, we are going to go through some stress and strain related examples. So the first example is, what would be the modulus of elasticity for a material that elongates 0.005 inches per inch when a stress of 145 ksi is applied? Okay, so we're looking for modulus of elasticity. What is the modulus of elasticity again? It's the slope of the stress and strain graph. It is stress divided by strain. So right here is the stress, 145 ksi, which is kips per square inch, and strain is elongation, and it is measured in inches per inch, which is kind of unitless, right? But it's really like a ratio. For every 1 inch of beam you have, it is elongating 0.005 inches, which is not a lot, right? That's kind of a small amount. Of course, if you have a beam that's 25 feet long, 0.005 times 25 feet times 12 inches, it's not like a crazy amount, but it's much more significant than 0.005, of course. So how would we solve it? Let's go back. Let's go back to the one that had Hooke's law right here. E is stress divided by strain. So all I'm going to do for this problem is take my stress and divide it by my strain. 145 ksi divided by 0.005 ksi. So do that with your phone or your calculator. I have 145 divided by 0.005 gives me 29,000. And what do you think the units are? Look, well, inches per inches is kind of unitless, so I have ksi left. So the answer is 29,000 ksi. That is the modulus of elasticity for this material, which happens to be steel. This is the modulus of elasticity for steel. Real number, and we're going to be using that number a lot. That's why I started with it. Let's go to example 2. A 120 kip axial load is applied to a 4-inch square wood post. The wood has a modulus of elasticity of 1,900 ksi. What is the resulting strain? Now, before we go any further, this is the actual modulus of elasticity for wood, 1,900. How does that compare to steel? Steel was 29,000. That's kind of how you know how much stronger steel is than wood, by the way. Okay. So I have a tensile axial load, meaning that I'm taking a member and then I'm clamping both ends and pulling it apart with a force of 120 kips. And that force is being applied to the cross section of this beam, which is a 4-inch by 4-inch square post, or 16 inches squared. So right there, I can get my stress, right? If I know that my force is 120 kips and my area is 4 times 4, well, stress is just force over area. So my stress is 7.5 ksi. Now that I know what the stress is, the question's actually asking you to find strain. So now I'm ready to go on to Hooke's law. E is given, that's 1900. We just calculated stress, that goes right here. The only thing left of our Hooke's law is the strain. So I'm going to rearrange the formula to get strain by itself. So I have stress divided by E, which is the modulus of elasticity, gives me 0.004. And what are the units for strain? Well, it's technically unitless, but we like to say inches per inch because it's a ratio. It could be miles per miles, really. Like for every 1 mile of pipe, you have stretch 0.004. It's just a proportion. Okay, so that's the answer to that one. Lost my place. So the next one is, how much would an 8-inch long, 4-inch diameter steel rod elongate if it experienced an axial load of 10 kips? So basically, let's imagine the scenario in your head. You have a rod that's 8 inches long, and then the top of it is a circle with a diameter of 4 inches. And then I'm clamping both ends and I'm pulling it apart with 10 kips of force. And I want to know, hey, how long is this rod going to be after I pull on it? So we have a few equations you can work with. The first equation is going to be the stress. Stress is force over area. The next one, it's been a while since we've done it, is the strain, which is strain is equal to the change in length over the original length, or the final length minus the initial length over the original length. So basically, let's use quick numbers. If I have a 10-inch rod and then after I stretch it, it becomes 11 inches, the strain is going to be the difference, which is 11 minus 10, which is 1, divided by the original, which is 10. So my strain would be 1 over 10, or 0.1 inches per inch. And then finally, the last equation is Hooke's law, which is that the modulus of elasticity is equal to the stress over the strain. Okay, so let's look at this first one. Ultimately, we're looking for how long the steel rod elongates. So which of these do you think we're actually trying to find? Like, what's my variable that I'm trying to figure out? How much it elongates. Well, an elongation is a change. So I'm actually going to be looking for, take a second, pause the video. I want you to guess, and I'll tell you the answer. We're actually looking for delta L. We are looking for the elongation, how much it's changing. So how do I get the delta L? Do I know what L is? Yes, I know that it's 8 inches. Do I know what strain is? No, do not know what strain is. I'm going to have to use what equation, what formula to get to strain. I'll have to use this. Okay, let's look at this. Do I know what E is? Yes, I do know what E is because it's a steel rod, and I know what the modulus of elasticity for steel is, or I could easily enough look it up. So I know what this is. Do I know what the stress is? No, I don't. But could I calculate stress? Yeah, I can. Because stress is just force over area. I know the force. Do I know the area? I can calculate easily enough. If it's 4-inch diameter, that's just a circle, pi r squared all day. Let's start with that. So first I'm going to get the stress. Once I get the stress, I'm going to plug it in here to get the strain. Once I get the strain, I can actually calculate the delta L. Okay, let's go. Find stress. Area equals pi r squared. R is just half the diameter, so 12.56 inches squared, which would make the stress around 8 ksi. We're rounding here a little bit. Now that I know what 8 ksi is, I'm going to plug this 8 ksi into this Hooke's law equation, which will give me my strain. E is 29,000 ksi for steel. If you don't believe me or you forget, Google it. Solving for strain gives me stress over E. Stress is 8. E is 29,000. Gives me 0.00027 inches per inch. Not a lot of change, right? But that's what the question's asking. Now that I know what the strain is, I got to figure out what delta L is. So I'm looking for delta L, which is going to be my strain multiplied by my original length, which is 0.00027 multiplied by 8, or 0.00216 inches is my change in length. Okay, how was that one? Let's do one more. Would a 700 kip tensile axial load applied to a 6-inch A36 steel pipe with a thickness of 1/2 inch be acceptable? Ugh, that sounds like a lot of words. But let's break it down. When we say acceptable, what we're really asking is the amount of stress applied too much for the member to handle? Do you remember what we use to determine if it's too much stress? We look to see which region we are in. Elastic region, good. Plastic region, bad. And then the difference between the plastic and the elastic region is, are you higher or lower than the yield stress? The yield stress for a material is really the strength of the material. It's how much stress it could handle. Are we applying more stress than it can handle? If we are, it's not acceptable. If we're applying less stress than it can handle, then we are good. Let's see how much stress we're applying and compare it to the stress that A36 steel can handle. So we have a pipe, which would suggest that there's an outer circle and then an inner circle. So that makes it a little bit different because the area is just a little bit more complicated. You're going to have to get the area of the outer circle and subtract the area of the inner circle. But once I get the area of it, all I'm going to be doing is doing the total axial load divided by the area to give me my stress. And that's the stress I'm comparing to A36 steel pipe. You might remember from a previous slide, A36 steel pipe has a yield stress of 36 KSI. So we have to make sure or check to see if the stress applied from this load on this pipe is more or less than that. So A36 steel pipe has a yield stress of 36 KSI. Therefore, the strength it can support is 36,000 pounds per square inch. We need to see what the applied stress is to verify it is less. So the area is pi r squared of the outer minus pi r squared of the inner. I think there's a typo here. Yeah, there's a typo here. Sorry, guys. I messed that up. I did the diameter right here. It should not have been diameter. So I'm going to fix that for the PowerPoint that you guys will get in the slides. I hope you can at least follow the logic. Let's just continue it out. I apologize for the typo, but hear me out with the logic. So now we know what the area is. Of course, the area is going to be different when I change it up. But once I know what the area is, I'm going to take the total for 700 kips divided by the area, gives me my stress. And in this example, this stress is higher than what is permitted, so it does not work. Again, I apologize that I messed that up, but I think you can understand the logic, right? We get the area, we take the applied load divided by the area, and then we're checking that against what the strength of the material is. Okay. So with that said, that's the conclusion of the first half of this week's lessons. Have a good one, guys.